Welcome to Algorithm Seminar. Today we're very happy to have Kimon to give the talk. He's an assistant professor in the David R. Charrington School of Computer Science and a member of its scientific computation group. Previously, Kimon was a postdoctoral fellow and principal investigator at University of California, Berkeley, in the Department of Statistics and ICSI. He worked with Michael Mahoney. Before that, he completed a PhD in optimization at University of Edinburgh under the supervision of Professor Jessica Ganzu. Kimon's most recent work focuses on machine learning on graphs, which is about making predictions using multimodal data sets that combine features and relational information among entities. Kimon's past work includes higher order optimization methods for machine learning and signal processing problems.
All right, thanks. So yeah, I'm glad to be here. And all right, let me start. So this is a work that this joint work with few people from the University of Waterloo. Amit actually is now at Huawei, but he was a former PhD student at Waterloo. So this is about a paper that has the same title, Graph Attention Retrospective. And so the talk is basically going to be split in two parts. The first part is going to be very informal. I will just try to give some intuition. And then the second part is going to be, details and some sketches for the proofs of the results that we have. So we are interested in relational data that are formulated as graphs. And here you see a simple toy graph that consists of nodes labeled from A to H and edges that connect the nodes. And in addition to the graph, we also have features that characterize the nodes. And in particular, every node has a feature vector here, which is denoted by X subscript by the name of the node. For example, node A has feature vector XA. And the goal is to do node classification, right? So we are interested in the simple problem of binary node classification. So there are only two classes. So during the talk, I'll be using interchangeably the same class edge and intra-class edge and different class edge and inter-class edge. So let's start with some basic graph neural architectures. So one of the most popular architecture for node classification, well, in general, actually, for other problems too, is graph convolution network, which is also known as GCN. And the core primitive of GCN is to do uniform averaging of the feature vectors for each node in order to obtain new representation of the input features. So, for example, here node A uniformly averages its features with its neighbors, nodes B and C. Now, if all nodes are in part of the same class, then this operation seems reasonable. However, it might be the case that nodes have edges where the neighbor is in the other class. For example, node C here has neighbor D, that's part of class 1, while node C is part of class 0. So in this case, it is reasonable to require the model to ignore the feature vector of node D. So graph attention actually was, people came up with this architecture to solve this issue. So issues like this, in particular, GATT, which is short for graph attention networks, introduces edge weights gamma, which are learnable parameters. So the learning process allows GATT to set gamma appropriately. And in this particular case, gamma for the edge between nodes C and D should be much smaller than same class edges within class 0. For example, gamma CA and gamma CB. And the reason that this is useful, as we'll see later, is because it allows GATT to classify the nodes perfectly at parameter regimes which are not possible by GCN. And yeah, we'll see some a lot of details about that in the coming slides. Okay, so we ask a very simple question. So our goal of this work is to understand how successfully can graph attention mechanism discriminate neighbors. So to figure that out, we will use a synthetic data model. In particular, the model that we'll use is called the contextual stochastic block model. And this data model consists of two parts: a Gaussian mixture model, which is used to obtain the features of the nodes, and the stochastic block model, which is used to obtain the graph. So for simplicity, we work with data models that consist of two classes, as I mentioned earlier, and each class has on expectation the same number of nodes. Okay, so let's start with the graph construction. The graph is represented using the random square matrix A, where a component of matrix A is a random variable, which is one with probability P if nodes I and J are in the same class, or it is one with probability Q if nodes I and J are in different class. And then we have the feature vector. So the feature vector xi of node I follows a Gaussian distribution with standard deviation sigma, and the mean of the Gaussian distribution changes based on the class of node I. So it is mu if it's class 0, and it is minus mu if it's class 1. And the means here and standard deviation are chosen for simplicity. Again, you can analyze different settings as well. So it doesn't have to be mu and minus mu. It can be general means. All right, so let me start describing the results, at least intuitively. So in this slide, we see a straight arrow that represents the distance between the means of the Gaussians. And we separate the distance into two regimes. The easy regime, which corresponds to distance larger than sigma squared log n, and the hard regime, which corresponds to distance smaller than k times sigma, where the parameter k here can be a constant or a non-constant, and each time we get different result, but it can be at most squared log n. So let's start with the easy regime. So in this regime, a classical argument implies that any multilayer network which only uses the feature vectors and no graph information can achieve perfect classification with high probability. At the same time, in this regime, GAT is able to discriminate same class from different class edges. And this means that the edge weights for different class edges are going to be significantly downweighted. What does it mean in terms of node classification? So this implies that GAT is able to perfectly classify the nodes independently of how close Q is to P. So in fact, actually, Q can be larger than P2. In this plot, you can see in the x-axis, we vary Q from a very small value to P05. We could have gone Q again bigger than P, but okay, I didn't do it here. But the result, the theorem holds for even in that case too. So note that GAT and no graph, meaning the MLP, are able to perfectly classify the nodes for any value of Q. On the contrary, the performance of GCN, which is not ignoring different class edges, you can see that it degrades as Q gets closer to P. So in the hard regime, and for non-constant K, the MLP with no graph will misclassify at least one node, while for constant K, the MLP will misclassify a constant fraction of the nodes. And now what can we show about the hard regime for GAT? So the hard regime is also where GAT starts to make mistakes on distinguishing same class and different class edges. And in particular, for non-constant K, GAT will not downweight at least one edge, while for constant K, GAT fails to distinguish actually a large fraction of same class edges from different class edges. In particular, we can show that 90%, where the fraction here, 9%, is kind of arbitrary. You can have any fraction, any constant fraction that you want. So, all right, so 90% of the edge weights are going to be roughly uniform, right? Which this is similar to what GCN is doing, where the weights for the same class and different class edges are going to be exactly uniform. All right, so this about GAT, this also implies that in the hard regime, node classification will depend on the parameter Q, the different class edge probability Q, as opposed to the easy regime where we showed that Q, the node classification result doesn't depend on Q at all. There's unfortunately for the hard regime for GATT, we were not able to obtain node classification result. I will explain later in the second part why, and I will also explain how we can get around it. And yeah, so however, we conjecture that in the hard regime, GATT's dependence on Q for perfect node classification will be the same as that of GCN. So informally speaking, this means that GATT is not going to be better than GCN for perfect node classification, for the particular data model that we're working with, right? Which it's a negative. It's basically a negative. That will have been a negative result, right? Because that means basically that the ability that GATT is giving you to learn attention coefficients, learn the edge weights, the model is not actually doing that in the hard regime. So in this plot, we show the conjecture. So you can see here that the performance of both GATT and GCN actually degrades as a function of Q. One is better than the other. We don't know exactly, so we cannot exactly characterize, when one's better than the other when you go beyond perfect classification results. Okay, so let's see empirically the behavior of gammas, right? These are the attention coefficients in GATT as a function of the distance between the means. So in this plot, you see the average gammas and the standard deviation as a function of the distance between the means. So the blue line with the star marker denotes the same class gammas, and the orange line with the X marker denotes the different class gammas. So you can see here that it is clear in the hard regime, meaning when the distance between the means is less than the standard deviation, the gammas concentrate around the uniform value that is 1 over absolute value of Ni, where Ni here is the set of neighbors of node I. So this is basically 1 over the degree of node I. And in this regime, meaning that in the easy regime, when the distance between the means is larger than the standard deviation, then it's when we start to observe the separation between the same and different class gammas, right? So in particular, the same class gammas are much larger than the different class gammas. For real data, we've actually run a lot of experiments on real data as well that you can find in the paper, and we observe similar performance for the attention coefficients. Okay, so let me now explain why this happens, like why GATT fails to get good attention coefficients in the hard regime, and why it works well in the easy regime. So, like there's the simple reason that GATT fails to discriminate neighbors in the hard regime, and to understand it, we're going to look first into how current graph attention mechanism works. In particular, what happens is that each edge is represented by. Is there a question? No.
Yeah. So, Kimon, I have a conceptual question. So, are there converses for these regimes?
Are there what? Sorry.
Converse results, basically inachievability bound results.
Oh, like information theoretic results?
Yeah.
There are information theoretic results for the contextual stochastic block model. But yeah, this is like for any method though, right? And
right.
But they work in a different parameter setting for the SBM. In particular, they work in the super sparse setting. When we'll see later what the exact assumptions that I'm making. They work in even sparser graphs than our results here. But yeah, like within the class of graph neural networks, yeah, we don't know. What's.
No, I mean, like if for example in the hard regime, the classification discrimination is information theoretically impossible, then the fact that GATT fails is
Yeah.
Expected. And that I'm just asking, so I don't know.
All the results that I'm presenting today are about perfect classification. So you either can achieve perfect classification or not, right? So, and yeah, so the if I remember correctly, the information theoretic limits that exist right now, they are not the same as ours. In particular, actually, they are very different. As we'll see, they are basically our results, our thresholds, right, are multiplicative. Like in particular, you want basically the p minus q over than something, as opposed to the information theoretic results. They are additive. You know, they basically ask for the spectral gap plus the distance between the means, where everything has been scaled in order to make that addition to make sense, needs to be bigger than something. So we have very theoretical, very different results actually. Ours multiplicative, the information theoretic results are additive. I'm not 100% sure how they compare, but yeah. And again, they are asking a different question, right? So the information theoretic results that exist right now, they are not about perfect classification. They are about doing better than random, right? So there are few things that are different there. There's they are asking a different question. They work with a different sparsity regime. Yeah, this makes sense.
Thank you. Yes, thank you very much.
Okay, so let me start again. So how does edge this edge attention works? What the models are doing is they are, each edge is represented by concatenation of the feature vectors of its nodes. For example, the edge between node A and B is going to be represented by the vector concatenated vector XA and XB. So then the learnable edge weights gamma, these are the coefficients, the attention coefficients, are parameterized using an MLP, which takes as input the concatenation XA and XB. So the problem of separating same class from different class edges reduces to separating the concatenated vectors. But in our case, the concatenated vectors also follow Gaussian distribution. So then this means that the problem of separating same class from different class edges basically reduces to classifying a Gaussian mixture version of the XOR problem, right? So if you don't remember the XOR problem, it looks exactly like the figure here, where we're trying to separate the blue from the red. So this problem consists of 4 Gaussians. The Gaussians are separated into same class and different class edges. So when the distance between the means is larger than sigma squared log n, then the data generated by the Gaussians are separable with high probability. However, when the distance between the means is less than sigma, then there is too much overlap. There's going to be too much overlap among the distributions, so that with high probability, the different class edges can be separated from the same class edges. And when I say again can be separated, I mean like perfect classification again, right? So yeah, so it's important to have that in mind. All right, so just a short conclusion before we go into details. So for this particular synthetic data model, attention is able to discriminate neighbors. However, this happens only when the graph is not really needed to perfectly classify the nodes. The reason that this happens is that the current attention mechanisms separate same class from different class edges by utilizing the unconvolved input feature vectors. But the problem is that when these vectors become very noisy faster than we start seeing any benefits from convolution. And we all these high level kind of results, we see actually the same performance on real data as well. And you can check the paper. I personally done a lot of experiments with real data as well, so we observe similar performance there too. Okay, so that brings me to the end of the first part. Are there any questions, or maybe if not, we can just move on? Okay. All right, so let's start. So let's assumptions. So the first set of assumption is that the intra-class and inter-class probabilities, meaning P and Q, the parameters of the SBM data model, we assume that there are like big omega log square n over n. This basically means that the expected number of neighbors is big omega log square n, and it also means that we have degree concentration. We also assume that P is bigger than Q. Actually, for I already mentioned this, for the easy regime, we don't need that assumption at all. P and Q can be anything. We did use that assumption for the hard regime, but I'm pretty sure that this can be replaced as well. At the end of the day, the only thing that matters is that if all nodes have the same connectivity pattern, you don't have to be, if everybody's connected to the other class, that's enough information and you can prove the same results as we're proving here. Okay, so what's the GATT convolution? So the convolution is actually the one layer, right? So the one layer convolution is shown here at the top, where what we are doing is we are averaging the transformed node features. So xj are the node features, w is the parameters that we're trying to learn, aij is the edge weight, and gamma ij is the attention coefficient, that is used to change the edge weight, basically. So we are doing this averaging for GATT, and gamma ij's are basically a softmax parameterized by the function psi, where the function psi is, for example, an MLP on the concatenated transformed node features. All right, so the first result on the easy regime, we can show that if the distance between the means is bigger than sigma squared log n, like little omega sigma squared log n, then we can show that we can find an attention architecture psi such that with high probability is going to perfectly separate intra from interclass edges, meaning that with high probability is going to solve this XOR problem that I showed earlier. This is the empirical version of the theorem. On the x-axis, we have Q. Y-axis is basically accuracy for edge classification. And this is the easy regime, so we can get 100% accuracy for intra and inter-edges. Okay, so here's how we prove that. Our goal here is to solve this XOR problem. And we can construct a psi function which does the following. The upper right quadrant and the bottom left quadrants are going to be set to a positive value, and the other two are going to be set to a negative value, right? So we can actually construct such a psi function. If you can do that, then basically you'll be able to classify with high probability separate the blue from the red. Now, the way that we do this is the way that we construct the psi function. We basically measure in correlation with one of the 4 means, right? So for the XOR problem, and if you are correlated mostly with a blue, then you get a positive value. Otherwise, you get a negative value. Okay, so yeah, that's how we prove that. And so how do we use this now to show something about the attention coefficients, the gammas? So again, if we are in the easy regime, the distance is bigger than sigma squared log n. Then if we use this psi function that I showed you earlier, then with high probability, we can show that the intra-edge gammas are going to be 2 over np, roughly 2 over np. And the inter-edge gammas are going to be little low, 1 over np plus q. This is basically 1 over the expected degree, and it's little low of that. So here's the theorem in the form of a plot. So the x-axis is again parameter q. Y-axis is the gamma value, and the blue line, which actually overlaps with the purple line, is basically the intra-edges, and you can see that the standard deviation is very small, so we have very nice concentration, around 2 over np. The orange line is basically the inter-edges, and you can see it's much lower, right? As the theorem says, much lower than the intra-edges. And just for reference, I also plotted the coefficients for the GCN architecture, right, which is the black line. Now, how we prove this result? So the psi function is a random variable, right? It takes as input the xi and xj, which are random variables. So we can show in the easy regime that the psi function actually concentrates. In particular, if nodes I and j are in the same class, then we can show that it concentrates to a large positive value where the magnitude depends on the distance between the means, which is the norm of mu. If I and j are in different class, then we have concentration to a large negative value. Right. So then, if we plug in this psi function into the gamma function, then we can show the result. And here's an example of it. So what we have? Okay, this is basically gamma with the psi function plugged in. And what happens actually is that you can see that the part that corresponds to interedges is basically 0. And so we're only left with the intra part, right? So you can easily see it's a simple calculation that this gives you basically that gamma ij's for intra edges are like 2 over np. For the interclass edges, we do the same thing, and this gives us that gamma ij's for interedges are lit low 1 over the degree, as I mentioned earlier. And yeah, so that's how we prove that. And now node classification for the easy regime. Again, if the distance is bigger than sigma squared log n, and if we use the psi function that I mentioned earlier, then we can actually show that we can achieve perfect node classification for any value of p and q, right? And the reason that q doesn't matter again is because, remember, those inter-edge coefficients are much smaller than the intra-edge coefficients. So here's the theorem in the form of a plot again. Actually, I showed this earlier in the first part. So here you can see that the blue line and the purple line, they achieve 100%, right? So the MLP GAT model achieves 100% accuracy. Same for the no graph, right? So this is the easy regime. We actually don't need the graph to achieve perfect classification. But GCN actually performance starts to degrade as Q goes close to P. Yeah, so here's the sketch for the proof. Again, if you remember, I mentioned earlier that the intra-class coefficients are much higher than the interclass coefficients. So when we plug those into the definition of the GAT convolution, then we get that the part that corresponds to the interedge is basically 0, right? So you're only left with the intra part. What does that mean, though, right? So we gave Gaussian input. So what output do we get? Well, we get something that it has actually reduced variance. That's what this convolution is doing. It in particular is reducing the standard deviation from sigma, which is what we started with, to sigma over square times np. And now if we compare this with the distance of the means, which is by assumption bigger than sigma squared log n, then you can see that the distance of the Gaussians is actually much larger than the standard deviation. And this is what allows us to show perfect node classification with high probability. All right, so that's about the easy regime. Let's go to the hard regime. So here, hard regime means that the distance is k times sigma. And here we can show that for any attention mechanism that takes as input the concatenated node features, then with high probability, we're going to fail. The psi function is going to fail to correctly classify at least 2 times phi complement of k squared, where phi complement here is basically the complement of the cumulative of the standard normal. Yeah, so right, so with high probability, we're going to misclassify a fraction of the interedges, right? And the exact misclassification fraction is given by this phi function that I've plotted here. So you can see that it drops quite rapidly. So for example, if you want like close to 50% of inter-edges misclassified, then K has to be around 0.25 or something like that. So here is the theorem in the form of a plot again. So x-axis again Q, y-axis is the classification accuracy for the edges. And you can see here that we, in the hard regime, we only get like 60% of the 60% accuracy for intra and inter edges. All right, so what about gammas, right? So what does that mean for gammas? And in general, it's difficult to handle this. So now we're going to focus on a very specific, very popular model, which is the original GATT model that has right now like 5,000 or 6,000 citations. So for that model, we can show that if you are in the hard regime, like meaning the distance between the means is smaller than k times sigma, then and if your parameters are constant, then with high probability, again, at least 90% of the gamma ij's are going to be roughly uniform. And the 90% is actually, again, arbitrary. Right? It can be 91 or 99%, and if this will only change the constant in that theta that is hidden in that theta. But the takeaway message here is that your attention coefficients are actually going to be similar to GCN. So there is no basically, and this is uniform attention, right? So basically no attention at all. So here's the theorem in the form of a plot again. So you can see that the gammas for intra-edges, inter-edges, even multiple heads. The original model actually comes with multiple heads. So the output basically means that you can have multiple outputs, and they use different gammas. Even if you use multiple heads, they're all going to be, the attention coefficients they are going to be very close to uniform. Right, so how do we prove that? Well, in the hard regime, the standard deviation is actually very comparable to the distance between the means. So basically, what that means is that the data acts like it's like noise. It's a Gaussian noise, and so that means that the data are not actually indicative of class membership. So given that fact, we can also show that a large fraction of the psi values are actually going to be constant in magnitude. We can show this actually using just simple properties of Gaussian random variables. So given those two facts, we get that a lot of gammas are going to be roughly uniform. All right. So yeah, unfortunately, as I said earlier, we don't have a result for node classification, and I will explain why in the next few slides. But here's the conjecture, and this is related also to the question that I was asked earlier. So the results that we get are multiplicative, right? So meaning that because we multiply, when you do the convolution, right? The convolution is basically some graph matrix times the features, right? This multiplication that you do results in a multiplicative result. And for node classification, the conjecture is that the result is going to be that if p minus q over p plus q times the distance is smaller than sigma times square root log n over the expected degree, then any single layer graph attention model will fail to perfectly classify the nodes with high probability. And the reason that I conjecture this is because, as I mentioned earlier, the attention coefficients are basically roughly uniform, which means that in the hard regime, the GATT model behaves like a GCN. And in another paper, we have shown that this is exactly the threshold that you get for GCN, right? So the conjecture basically is that you're going to get exactly the same performance in terms of when you ask the question of perfect classification, you're going to get exactly the same performance as GCN, which is captured here by this threshold. Okay, so again, the conjecture in the form of a plot. I've shown this plot again in the first part of the talk. Here you can see that the important thing to notice is that for both GAT and GCN, what the parameter Q is and how close it is to P, it really matters. Both models are affected by interedges. Right. So what is the issue, right? That we cannot prove that conjecture. The issue is that there are technical difficulties due to correlations between the attention coefficients and the node features, right? Remember, the attention coefficients gamma, they take as input the node features. So then you multiply the gammas with the node features, and then and then it's the output. It's a nonlinear function of a Gaussian. And we don't know how to deal with this. There's an important result that is missing from the high dimension probability literature that at least I don't know. I couldn't work around it. I couldn't find a result which basically the result is like if you are familiar with this, something called the Sudakov minoration result. So it allows you to work with Gaussian processes that are. What is missing is that we cannot work with Gaussian processes that are nonlinear functions of Gaussians. They can. Yeah, so we don't even have a result for sub-Gaussian. So anyway, I can discuss the details later if anybody is interested. So the fix that we thought about it is just, in order to break this correlation, the fix that we thought about is just consider an independent copy of the node features that we pass to the attention mechanism. So this will allow us to make the attention coefficients independent of the node features while conceptually, we are basically solving the same problem. So in this case, we can actually show the conjecture that, when the distance between the means of the edge features, that independent copy that I talked about, if the distance is small, then what you get this GCN performance. All right, so another question that we have been working on is, can we do better than GCN? And the answer is yes. You can actually use additional features that you can obtain from the graph. For example, you can take the eigenvectors of the adjacency matrix, and you can pass those into the attention mechanism. So even if your node features are noisy, but if your graph is clean, meaning that you have this gap here, that the absolute value of square root p minus square root q is bigger than square root 2 times log n over n, then we can actually show that you can still achieve a perfect node classification if the distance between the means is sigma square root log n over np. Now this is better than GCN. GCN actually in the denominator has np plus nq. So it's slightly better than GCN. However, and here's the catch, that if you have such a spectral gap in the adjacency matrix, then you can actually prove you can do perfect classification just by using the eigenvector, right? So you don't need the features at all. So okay, we can get something better than GCN, but still, at least for when you ask the question of perfect classification, we're not, it's just, you can just do community detection. So that's that. Right, so can we do better than a simple community detection as well? I believe the answer is yes. There are no results actually of that flavor. And I think what happens is that you need to go beyond the question of perfect classification. And when you go beyond the question of perfect classification, you've got to remove the assumption on the spectral gap on the graph. Now, if you remove the spectral gap on the graph, then it's where it makes sense to combine the graph with the features, right? Because using both of them together might be better than using each one of those in isolation. But yeah, there are no results of that type. If anybody is interested to talk about it, I'll be very happy to talk about that. And yeah, so that brings me to the end of the talk. And thanks a lot for your attention.